In this video, we'll go through an example of the application of Monte Carlo simulation to a hypothetical manufacturing problem. The example that I'm using is based on a model from Anthony's son, who's given permission to use this model. Note that the web address that I have here is no longer available. I've been using this example for quite a few years, so I'm not exactly sure where it is now, but that was the original reference. And I haven't been able to find a cleaner example or create my own that's not just a clear copy of this one. So I'm going to continue using it. So here's the basic problem. A firm is considering producing and selling a new product under a pure perfect market condition, and the firm wants to know the probability distribution for the profit associated with the product. So this notion of a pure perfect competition market basically says that the firm can't influence the price, can't influence the market in any way. So for our example, the total profit is given by the following equation. Q times P, where Q is the quantity sold and P is the sales price per unit. So Q times P represents the revenue, minus Q times V, which is the variable cost per unit plus the fixed cost. So this is the cost. So we have the revenue minus the cost, and we can also represent this in its short form as Q times P minus V minus 5,000, which is the form that we're going to use throughout the rest of the exam. So note, for this problem, we're considering doing this project sometime in the future. So many of these, or several of these quantities, are unknown. So for example, we're not exactly sure how many we're going to sell. We're not sure what the price is going to be, again, under this assumption of pure perfect competition. And we're also not sure what the variable costs will be. We probably have a pretty good handle on the fixed costs because, again, the fixed costs are all upfront costs. And so we're going to represent this uncertainty with Q, P, and V, indicating that they're random variables. So we're going to assume Q is uniformly distributed between 8 and 12,000. So essentially, our Q looks like this. Here's Q, 8,000, 12,000, F of Q. And the P and V are both normally distributed. So we'll have here, let's see if I can draw these both here. So we have the variable cost at 7 and normally distributed with a standard deviation of 2. And for, this is variable cost, and this is F of variable cost. And for the price, 10, standard deviation of 3. This is P, and this is F of P. And so when we look at our equation, our expression for total profit is equal to Q times P minus V minus 5,000 from the previous page. Because Q, P, and V are all random variables, that tells us that total profit is also a random variable. And so we have our total profit looks something like this. Let's say this is TP and this is F of TP. Oops, that's pretty ugly there. Let me try that one more time. That's F of TP. And so I really don't know anything that it looks like. I'm just making a guess here. We have some mean value of total profit. We have some standard deviation of total profit. And we really don't know anything about this value and where that is with respect to the origin here. And so what we'd like to do is use Monte Carlo simulation so that we can characterize this distribution of total profit. So I'd like to be able to use Monte Carlo simulation so I can estimate this distribution and its corresponding parameters. So before we get to the Monte Carlo simulation, I will note that one thing we can do is we can get the expected value of total profit if we simply apply the corresponding expected value of Q and so on. So I would have the expected value of Q times the expected value of P minus V minus 5,000. And so this is going to end up being my expected value of Q is 10,000. The expected value of P is 10. Expected value of V is 7. And so my expected value of total profit is 25,000. And so that's what we expect to see right here under my mean of my unknown distribution. So if my only decision criterion on whether or not to make the product is the expected value, then there's really no reason to use Monte Carlo simulation because I can compute that directly. On the other hand, if I'm interested in other parameters of the distribution, for example, maybe I'm interested in the standard deviation, or I'm interested in the probability of losing money, or I'm interested in the upper fifth percentile or something like that that would incorporate the risk of the decision, that's where Monte Carlo simulation would become useful. So let's have a look at the general Monte Carlo. The general Monte Carlo method in an, see if I can write that a little bit better, method in an algorithmic form. So the basic process that we do when we use Monte Carlo simulation is, let's say we're going to store the results. And let's just say we're going to store the results in a list. Then I'm going to, for I in range in reps, where in reps is the number of replications, I'm simply going to compute the value, or sample a value actually. Value equals sample, and then I'm going to store that value. Results append value. So I execute I sample from my population a number of replication times, and I store all of those individual values, and in the end, analyze results. And how I analyze the results really depends on the problem that I'm solving. So I might want descriptive statistics. If I can spell descriptive statistics, like the mean, the standard deviation, and so on. I might want the empirical probability distribution, so like a histogram, for example, and so on. So again, what specifically I do in terms of analyzing results depends on the problem that I'm solving. Of course, the sample is the key to the specific Monte Carlo simulation that we're doing. So this methodology that we see here is very general, and we solve basically any Monte Carlo simulation can be cast in this structure. And for our problem, sample is simply going to be sample a Q from a uniform distribution between 8,000 and 12,000, sample a P from a normal distribution with a mean of 10, standard deviation of 3, sample a V from a normal distribution with a mean of 7, standard deviation of 2, and then return Q times P minus V minus 5,000. And so this is our expression of total profit. And so the sample function here, the sample subroutine, is essentially equivalent to reaching into the population and pulling out one independent sample. And when we go in our in-reps loop, that's equivalent to drawing a random sample of size in-rep of observations of our random variable. So our task now at hand is to code this Monte Carlo simulation in Python. So let me jump to the code here. You can see here's the function. It's called MFG. Actually, it's called MFG underscore hist because I've added the histogram, as we'll see in just a second. And you can see in our code, I've got a comment structured here where I define some initial parameters. I define up front the number of replications, so I'm going to run for 100,000 replications. I define the number of bins in the histogram. I want to do 35 bins. I also have what I call the debug flag. If you set it to 0, it doesn't print intermediate results. If you set it to greater than or equal to 1, then it's going to print intermediate results. So we basically have a single function here, our sample function, which is pretty much an exact copy of what we had in the algorithm, in the pseudocode, except I've replaced the uniform and the normal random variates with the corresponding methods from the Python random module. So to get a random uniform, it's just random.uniform. To get a random normal, it's random.normal variate. So you can see I sample Q, I sample V, I sample P, and then I return the profit value. From our model, we initialize our results. Then if we're going to show the intermediate results, we print a note. Otherwise, we skip it. Then we replicate. We compute a sample. If we want to see the intermediate results, we print it. Otherwise, we just append it onto our results. So when we come out of this loop, TPS has all of the individual observations from, in this case, our 100,000 observations. So we compute some descriptive statistics here. I compute the average value, so I just float the sum of TPS divided by replications to give us the mean. Then I print the values. So in this case, I'm specifying how many replications I did, and then I print three things. I print the average, which I just computed. I'm also interested in the range, which is the minimum value, maximum value. So I just use the min function over our TPS list to get the minimum, the max function to get the maximum. And finally, I'm also interested in the probability of losing money. So the probability of losing money is equal to the proportion of observations where the total profit was less than 0. So I use a comprehension here that just says V for V in TPS. So this pulls out the individual values of TPS with the filter if V is less than 0. So this inner list right here will include all the observations of total profit that are less than 0. I can then simply use the length function to get the count of the number of times that occurred, divide that by the replications, and get that expected proportion below 0, or probability of losing money. And then the final part of our code, we create the histogram. So I use the backup here. I'm not sure I mentioned this before, but I use matplotlib, defined as PLT. So I create the histogram. I then am interested in the sample mean relative to the 0 point. It's going to indicate where I start losing money, so I just added 2 lines to that, to the histogram to illustrate those, and then I show the histogram. So if we go execute the code, mfg hist Python, you can see that the average that we got from our 100,000 replications is 24,972. Of course, we know the true value here of 25,000. So I compared this to the true mean, and it looks pretty close. I can then look at the range, and this says that I had at least one observation where I lost $148,000. Probably pretty bad. I had one observation where I made at least one observation where I made $192,000. That's pretty good. And so here is our estimate, our empirical probability distribution. And we look at this probability of losing money of approximately 24.4%. That's roughly this area to the left of the 0 line. So if I could integrate this function, or if I could integrate this distribution somehow from negative infinity to 0, this area here would be 24.42%. So from a decision-making perspective, in other words, whether or not I should make this product in this case, the probability distribution, or the empirical probability distribution, provides me a lot of additional information. Again, I computed the sample mean right here at 25,000, and in isolation, the sample mean of 25,000 looks like a reasonable return. However, when I incorporate the fact that there's a fairly high probability of actually losing money, then I might want to rethink that decision. So I don't want to imply that if there's a high probability of losing money, you would never make the decision. Simply that having that additional information that the probability distribution gives us lets us make a more informed decision. And so through the use of Monte Carlo simulation, as you see, it's fairly simple to get this probability distribution estimate.